Good morning, friends. Today we'll look at the problem insert, delete, get random in constant time on average. So what we are trying to build is a data structure which can provide us a constant time for insertion, constant time for deletion, and constant time for retrieving a random element from it. Now, of course, there are some APIs that we have to build. Before we go that, first let's understand how do we use or how to use the existing data structures to build this new collection to support these operations. We'll look at some of the data structures that we are fairly familiar with. One is arrays, linked lists, dictionaries, trees, graphs, etc. We know that certain data structures perform some operations in constant time, some operations in logarithmic time, some operations in linear time. Let's say for an example, take arrays as an example. We can insert an element in an array at the end in a constant time on an average. Of course, if the array size is bigger than if your element after inserting the element, if your array size is crossing, then you have to resize the array. That would take a copy of order of n. But on an average, we can consider the insertion of an array element in an array is a constant time, and removing an element from an array is like can also be done in a constant time by doing a swapping between the element at that index to the last element, but provided that you don't need to manage the elements in the array in a sorted order or in any order for my matter. And of course, indexing, identifying an element in an array can be done in a constant time by having the index of that element in the array. And similarly, linked list, if you take linked lists are also a linear data structure, but the elements in the data structure are present distributed in the memory and they are connected via pointers. So yeah, it's the linked list itself allows you to insert an element at any position in a constant time, which arrays can't give you. But and you can extend the linked list to as big as possible till your size of the memory available on your system. But the problem with linked list is that it doesn't have ability to identify an element in a constant time. So you have to traverse through the list and understand where that particular element is present. So linked list fails in the idea of identifying or retrieving an element from its collection in a constant time, but arrays can do it. Now, dictionary is a data structure which you can insert, you can retrieve an element in always in constant time. Let's also evaluate trees and graphs. We know for sure that even in a best case of balanced binary tree, then your time complexity of insertion, updation, and deletion would always take a logarithmic time. For that matter, graphs are also similar to trees, but graphs, maybe you start graphs and you add nodes to the graph on dynamically, but you need to do, depending on the use case, you have to manage your state of the graph. So they both pretty much deal in logarithmic time. So, but the problem that we are talking about requires a constant time. So having said this, so we need a way to have a quick insertion, quick removal, and randomly retrieving an element from the collection. These are the three things that we have to solve for. So we will use a combination of data structures to solve this problem. This is my proposal. We will use an array and we will use dictionary to solve this problem. And arrays, we can add or remove an element at the array in a constant time and space. In this case, this is useful because the problem never didn't ask us to maintain the order of the elements in which they are inserted. So we can insert an element at the end of the array. So arrays can help us do this in constant time. Now retrieving an element, given a value, you want to retrieve an element. Since arrays by itself are not managing whether it doesn't manage where this particular value is present in the array. So we need another data structure to give us a mapping between given a value in which index the element is present, where dictionary comes handy. So we will use a dictionary to store the value and the position of that value in the original array, in the array. So that's how we solve the problem of retrieval. Now let's get to the problem of random. You want to run a random, you want to generate a random number and retrieve the value. So since arrays are linear data structure, we know the length of the array at any point of time, and we generate the random number between 0 to the length of the array. We get an element, we get a position. Once we get the position, we will simply return the value. That's how we manage. Let's look at removal of the array. How do you remove an element? So remove is an operation. You're given a value, you have to remove the element from the collection. Now by taking the value, we can look at first in the array, understand that the elements, by looking at the value, I will in the map I can know at which index this particular value is present. So we'll go to that index in the array and swap the value of that index to the end of the array with the element in the end of the array. So what happens is this particular value will move to the end and the end value will come into this particular index, and we just resize the array. And in the dictionary, what we are going to do is we are going to do two operations. One is delete the actual value, and second thing is update the value which is at the end of the array to the update the index at the end of the value to the updated index. This is how we are going to solve this problem. Let's look at the solution that I have already written. So this is already submitted. I'll just refresh it and we'll explain. Okay, give me a minute. Yes, let's look at the step by step. So the default, this is how we're going to implement this. So we are going to have a dictionary and an element array. So this is where we are actually storing the values of the collection, and this is a this is a helper data structure that is going to manage the mapping between the value and the index at which this particular value is present in the elements variable. Now the constructor is going to initialize the data structure, and then let's look at insert, remove and get random functions. Insertion, as we discussed, first we were going to check whether the given value is already present in the collection or not. If the given one is already present, that means we are not going to insert, and we are going to inform the caller that this is already indexed by returning a false. If the element is not already present, then what we are going to do is we are going to append the element to the list, and we are going to resize and we are going to update the dictionary to keep the value at the index at which the particular element is going to be present. In this case, if you observe, what we are doing is we are appending the element at the end of the array, and we are updating the dictionary to keep that mapping. Now see, let's use this idea and see how we are retrieving a random element before we remove any elements. Now what we know is the length of the array, and then we identify an index by doing a modulo of L. So it will generate a constant, an index between 0 to L. Once we have the index, we will return the value at that index. Thus this is a randomly generated position, randomly generated value, and this is happening in a constant time because randint is a constant thing, and retrieving an element from an array is also a constant operation. Now let's look at the interesting thing, the removal of the element, removal of a value from the collection. To remove, first we need to understand whether a particular element is already present in the collection or not. So that's what we are going to do. We are going to look up into the dictionary and see if the particular value is present. If it is not present, then we are going to return false. If this is present and the dictionary is going to get empty, what we are going to do is, this is if the elements are less than 2, that means there is a one element or a no element. What we are going to do is, one element I am going to reset my data structures to have an empty list, so there are no elements in the collection, and delete the value in the dictionary, and then simply return true. If the elements are more than that, then what I'm going to do is I'm going to identify the last element, and this is going to be swapping with the index that we will identify. So we have identified the index in this position. So let's take an example of 2. If 2 is present at index 1 and the length of the array is going to be 10 for a moment, then swap element at the element 10. You have a let's say at the index 10 we have an element called element value is 15. Then the swap element is 15, which now is going to be go into the index of 2. That's what this is. And then this elements dot index. So now what we are going to do is in the actual virginal array at that particular index I am copying the swap element, and the element that is already present I am resizing the element and I am deleting it from the dictionary and returning true. And if you just submit, this is how it is. So let's look at the time complexities. Of course, the problem itself is asking for order of 1 on average. So insertion is happening asymptotically in constant time, but not always. Reason being, the append function will resize your array if your element is more than the capacity of the array. Um, this is in Golang. Even if you take Java or C++ implementation of dynamic arrays, they have to resize the array in order to accommodate the elements that are coming which are more than its size. Now let's look at the get random function. We already talked it's a constant operations. Random is a constant operation and retrieving an element from an array is also constant. Let's look at removal. Removal is happening also in constant operation because the lookup is happening in constant time from the dictionary. If it is already there, what we are going to deletion is also in constant time, and swapping is a constant operation. Thus this whole removal operation is a constant operation, and insertion is the only one asymptotically constant, because over longer, as the array size keeps growing and growing, the number of elements that comes in can accommodate, because every time we resize the array we are going to double the size of the array, so that as the size of n grows, when you double the array, what happens is asymptotically your array is so big to accommodate any new number of elements that are coming in. That's the idea. That's all I have. I'll leave it. One thing is to call out for this. We are using a data structures called elements and lookups. So both of them uses an order of an extra space to store the elements and to manage the elements. So time complexity is constant and space complexity is order of n. There could be algorithms where you can use more space complexity, because the problem has not restricted us to use any hasn't commented anything about the space complexity. But to leave one comment from my side is that arrays are a little tricky because they are consecutive in memory. So scaling up to, if you're really having huge data, then we can't fit that in a single array. Then we have to use a different style of map reduces or something like that to manage these elements in a different systems and then correlate to generate this behavior. That's all I have, and thank you very much.